dive with us into the vortex of a groundbreaking experiment that has managed to replicate the rotation of black holes using a superfluid helium vortex. This experiment, detailed in the esteemed journal Nature, has been a revelation, showcasing near-frictionless dynamics eerily similar to black hole rotation. The team at the University of Nottingham used superfluid helium, a peculiar state of matter that behaves like a fluid with zero viscosity. This allowed for the observation of surface waves within the vortex, an uncanny replication of celestial vortices. This endeavour, though complex, isn't just about black holes. It's about bridging the gap between general relativity and quantum mechanics, two pillars of modern physics that have been notoriously difficult to reconcile. The experiment offers a tangible way to probe the quantum nature of black holes, opening a new pathway to unite these two disparate branches of physics. But how does this experiment work? The core of the operation lies in the behavior of the superfluid helium vortex. As it rotates, the superfluid generates quantized vortices, miniature tornadoes of sorts, that mimic the gravitational conditions near rotating black holes. These vortices, akin to miniature black holes, exhibit surface waves that mirror the behavior of celestial vortices. Black holes are some of the most fascinating and mysterious objects in the universe. They are regions in spacetime where gravity is so incredibly strong that nothing, not even light, can escape their grasp. Here's a breakdown of what we know about black holes: super-strong gravity. Imagine squeezing a giant star several times its size into a tiny point. That's the immense density that gives black holes their powerful gravity. Event horizon, the boundary around a black hole where the escape velocity, the speed needed to escape, exceeds the speed of light, is called the event horizon. Once something crosses this point, there's no turning back. Formation. Black holes are born from the death of massive stars. When a star runs out of fuel, its core can collapse in on itself under its own weight. If the core is more than about 3 times the mass of our Sun, the collapse continues unabated, forming a black hole. There's another theory for supermassive black holes, which are much larger, but their formation process is not fully understood. What we can't see directly. Since light can't escape a black hole, we can't directly observe them, but we can detect their presence by the influence they have on surrounding matter. For instance, material swirling around a black hole can heat up and emit bright light before falling in, creating a signature that astronomers can use to identify them. Understanding black holes. Scientists are still unraveling the mysteries of black holes. There are many unanswered questions about what happens beyond the event horizon, and how black holes interact with the universe around them. The implications of this experiment and its findings are vast for the field of black hole research. It paves the way for a deeper understanding of these cosmic enigmas. Furthermore, it has the potential to revolutionize other fields beyond astrophysics, such as superconductivity and technology development. The global market for quantum physics research is expected to flourish, fueled by groundbreaking experiments like this one. Here are 5 famous sci-fi movies that revolve around the topic of black holes. Interstellar, 2014, directed by Christopher Nolan. This movie explores the concept of a wormhole near a supermassive black hole as a means of interstellar travel. The visual depiction of the black hole gargantua and its intense gravitational effects was lauded for its scientific accuracy. Event Horizon, 1997. This horror/sci-fi film follows a crew investigating the reappearance of an experimental spacecraft that was designed to create an artificial black hole as a means of faster-than-light travel. The movie explores the terrifying consequences of tampering with such powerful cosmic forces. The Black Hole, 1979. One of the earlier mainstream movies to feature a black hole. This Disney film follows a crew of space explorers who encounter a lost ship trapped in the gravitational pull of a massive black hole. Star Trek 2009. In this reboot of the Star Trek franchise, the villain Nero emerges from a black hole and creates an alternate reality, setting up the new timeline for the rebooted movies. Lost in Space, 1998. While not the central focus, this adaptation of the 1960s TV series features a pivotal scene where the Robinson family's spacecraft becomes trapped in the gravitational pull of a newly formed black hole. These movies have used black holes as a narrative device, exploring the mind-bending physics, potential for space exploration, and existential dangers associated with these cosmic phenomena. While it is not possible to create a full-scale black hole in the lab, scientists have been able to simulate certain aspects and dynamics of black holes using various experimental setups and techniques. Here are some ways researchers have aimed to study black hole physics in the laboratory. Analog black holes. These are systems that can mimic some properties of black holes by using materials that allow the formation of event horizons for perturbations or waves. For example, experiments have been done with fluids, ultra-cold atoms, or non-linear optical systems to create effective event horizons and study Hawking radiation analogues. Quantum simulation. By controlling and manipulating quantum systems like ultra-cold atoms or trapped ions, researchers can create systems that may exhibit dynamics similar to those found near the event horizon of a black hole. These quantum simulators allow testing theories about the extreme gravity environments near black holes, Bose-Einstein condensates. These ultra-cold clouds of atoms can be used to simulate aspects of curved spacetime and gravitational fields. By manipulating the condensates, scientists have observed phenomena akin to frame dragging and ergo regions around rotating black holes. Tabletop experiments. Simple setups using materials like silicon, light, or fluids have been used to mimic certain characteristics of black holes, such as the bending of light or the formation of vortices that resemble the dragging of space-time. While these experiments cannot reproduce the full complexity of astrophysical black holes, they provide valuable insights into testing theories of gravity, quantum mechanics, and thermodynamics in regimes that are difficult to probe directly through observations. Here are 3 mind-boggling facts about black holes. Spaghettification. If you were to fall into a black hole feet first, the difference in gravitational force between your feet and your head would be so extreme that you would literally be stretched out into a long, thin strand of molecules, like spaghetti. This process is known as spaghettification, and it would happen before you even reached the event horizon of the black hole. Time dilation. Due to the intense gravitational force of a black hole, time itself would appear to slow down the closer you get to the event horizon. From the perspective of an outside observer, if you were to approach the event horizon, you would appear to move more and more slowly until you seemed to freeze at the horizon itself, never quite crossing it. Holographic principle. According to the holographic principle, all the information contained within a black hole's event horizon is effectively encoded on the two-dimensional surface of the horizon itself. This means that the three-dimensional world we perceive may be effectively holographic, with all the information describing a region of space being encoded on its two-dimensional boundary. This mind-bending concept challenges our fundamental understanding of how information and dimensions work in the universe. These facts illustrate the extreme and bizarre consequences of the immense gravitational forces present in black holes, which push our understanding of physics and reality to the limits. As we venture deeper into the quantum realm, the secrets of the universe reveal themselves in the most unexpected ways. So, as we stand on the precipice of this new era in black hole research, remember this. Even in the depths of a laboratory, we can touch the stars. The universe, in all its mystery and grandeur, is within our grasp. Thanks for watching this episode of Sci-Sips. Do you have any lingering questions? Leave a comment below and hit that subscribe button to find out in the next video. Remember, don't let your thirst for knowledge go dry. Smash that like button and subscribe to Sci-Sips for more mind-bending science content.